In this lecture, we're going to talk about arrays. What do we mean by an array? Well, generally, it's just a collection of numbers or variables or strings or objects, and just organized in some fashion. It's just a way to organize a bunch of things. So that's kind of at the high level, abstractly speaking. It's a bookkeeping technique. But in practice and applications, especially for engineers, they're most important when they're used to represent the entities that appear in linear algebra, matrices and vectors and things of that nature. And in those cases, they can have physical significance. They can represent a stress matrix or a force vector and things like that. So for right now, we'll get to linear algebra in a bit, future lectures. For right now, let's just look at manipulating arrays, getting numbers into arrays, and doing essentially the bookkeeping part. So let's say A is equal to, now to enter an array, we put the left bracket sign and then some numbers. And let's separate the numbers by commas here, 1, 2, 3, 4, and then right bracket closes the array. That produces a row vector, 1, 2, 3, 5. What if we did B is equal to left bracket 1, semicolon 3, semicolon 4, semicolon 5, right bracket, enter. Now we get a column vector. The 4 elements, 1, 3, 4, 5, arranged in a column. What if we combine those? A is equal to 1, comma 2, semicolon 3, comma 4, right bracket, enter. Now we get a 2 by 2 array. So we can see what happens here. This is an element 1. Comma means go to the next column. 2 goes in the next column. Semicolon means go to the next row. So we go down to the next row. A 3, comma, next column, 4. Okay, so we could say x is equal to 1, semicolon 2. That should make a 2 row by 1 column vector, a column vector. And then, by the way, we could say y is equal to a times x. And we get a 2 row column vector with elements 5 and 11. Where did the 5 and 11 come from? Well, they came from the operations of linear algebra, this matrix times this vector. Okay, so that's, again, where we'll mostly be using these ideas. But we're not going to get into linear algebra in this lecture itself. Now, there are some variations on these ways of entering elements in a matrix. Let's say B is equal to left bracket 1 space 2 return 3 space 4 right bracket return. That enters a 2 by 2 array. So we can, instead of using commas, we can use spaces, and instead of using semicolons, we can use carriage returns or the enter key. Okay, so that's just a variation. Right? U is equal to 1, comma 2, comma 3, or V is equal to 1 space 2 space 3. Now, sometimes using the white space, the just blank space, or the carriage return are very convenient for entering these arrays in when you're using the keyboard. But generally, especially in writing a program, you want to explicitly use this notation where you have commas to separate columns and semicolons to separate rows. It's much more meaningful to the reader and clear, and you're less likely to make errors. One of the problems can be, like if you have in a program V is equal to 1 space 2 space 3, you can be editing and accidentally do something like this, and now you've got just 2 elements, 1 and 23. If you're explicitly putting the commas in there, it's much clearer that here you've got 2 comma 3, and here you've lost the comma and you just got 1 comma 23. Alright, so you can initialize arrays, you can form them by just directly entering the elements. So a name for the array equals left bracket, and then just start on the first row, 1, 2, 3, 4, semicolon, the next row, 5, 6, 7, 8, and when you're done, the right bracket, and there you go. Now that can be a little tedious, and in fact, most of the time we will use arrays that we generate in the computer. We don't manually enter them. But there are some kinds of arrays that we want to generate time and time again, and we want a shortcut for doing that. A very common one is to have an array of zeros. So look at this. A is equal to zeros, 2, comma 3. That's going to be an array of zeros with 2 rows, 1, 2, and 3 columns, 1, 2, 3. How about B is equal to zeros, 3, 2? Well, that's going to have 3 rows, 2 columns. Another thing we often want to do is create an array with all ones. So we could say B is equal to 1s, 3, 2. Same dimensions, 3 rows, 2 columns, but filled with all ones. So C is equal to 1s, 3, 3, a 3 by 3 array with all ones. Now another very common type of matrix we want to generate is the so-called identity matrix. So for example, from your linear algebra, you know that if you have a matrix that has 1s on the diagonals and 0s off diagonal, that's an identity matrix. Okay, so all 1s on the diagonal. Well, we could enter it brute force like this with all the 1s and 0s, but we do that so often that there's a special command, the EYEI command, I for identity. So then just put the dimensions 3 by 3, and we generate that automatically. By the way, it doesn't have to be square. A true identity matrix, of course, has to be square, but the same command can more generally create a matrix of arbitrary numbers of rows and columns, and it will put 1s on the diagonal elements. It's just that there aren't as many diagonal elements as there are either rows or columns. So in general, there'll be more rows or more columns than there are diagonal elements, right? If we went the other way, 5, 3, we'd still only have 3 diagonal elements, but we have 5 rows. More generally, so let's see here, I, 3, 3. What if we want a diagonal type matrix, but we don't want all 1s on the diagonal, sorry, but we want some specific numbers? Well, there's a command called diag, and then just give an array that gives the element you want on the diagonal. Say 1, 2, 3. And there's a diagonal matrix with 1, 2, and 3 on the diagonal. Conversely, if we have a matrix, let's see, A is equal to, let's do this guy, 1, 2, 3, 4. If I say diag and an existing matrix as the argument, it'll strip out the diagonal elements, 1 and 4. All right, so we have here some various matrices of different sizes and with different types of elements. What if we want to know the size of a matrix? Obviously, we can print it out and count. Here, C has 1, 2, 3 rows and 1, 2, 3 columns, but there's also a command, size of C, 3 rows and 3 columns. How about B? Well, size of B should have 3 rows and 2 columns. Okay, so the size command gives you the dimensions of the array. What if, for B, I only wanted to know the number of columns? I didn't care about the number of rows. Then I could do this. Size B, I just want to know the number of columns. So quote the character C for number of columns, 2. Or if I want the number of rows, quote R. Now, vectors, which are a special case of matrices, for example, V is equal to 1, 2, 3 with semicolons, it'll be a column vector. I can of course say size of V, and it'll be 3 by 1. The 1 here is kind of redundant. I know it's a vector, so I just really want to know just the number of elements in the array. There's a shorthand for that. Length V, 3. There are 3 elements in the array. Likewise, if U is equal to 1, 2, 3 separated by commas, which would be a row vector, length of U will be 3. How about A? What is the length of A? 4. It's the total number of elements. B here, length of B. Well, B is 3 by 2, so there will be 6 elements, and so on. Sometimes you want to generate a matrix that has random elements. Maybe you want to test an algorithm and you just generate some, you simulate some random input or something. So there's a command, rand, and then give the dimensions. Let's say we want a 3 by 2 matrix of random numbers, and there you go. The numbers are uniformly distributed between 0 and 1, so they will be inclusively between 0 and 1, and any value is equally likely as any other value. If I run that command again, notice I get a different array. Every time I run the random command, I get a different set of random numbers. If I wanted different size, right? I just put in like 4 by 2 and so on. Now suppose I have this matrix B, all right? What's the size of B? It's 3 by 2, and I want to generate a random array of the same size as B. Well, I could figure out the size of B and then say rand 3 by 2. But there's a shortcut for that. Rand B. That means generate a random matrix that is of the same size as B. Here's A, 2 by 2, rand A. Or how about an identity the size of A, or ones the size of A, and so on. So there's a shorthand. I can just put a matrix or a general array as the argument, and Scilab will generate the corresponding type of array, identity or ones or random or what have you, of the same size. Another very common operation is to generate an array, especially vectors, of uniformly spaced elements. So for example, t is equal to, this might be an array of time values, say 0, comma 0.1, comma 0.2, comma 0.3, comma 0.4, comma 0.5, 0.6, comma 0.7, comma 0.8, close array. And there are an array of, say, time samples. Now that was a lot of work. It'd be nice if there was a shorthand for that, and there is. Look at this. T is equal to 0, semicolon, 0.1, semicolon, 0.8. What does this mean? This means form an array which starts at 0. The next element after the first semicolon is the increment. So each element increments by 0.1 and continues until you reach 0.8. Hit enter, and there you go. I could also have put that in. Let's say s is equal to, I could put it in inside the array brackets 2, either way. Okay, so that generates a uniformly distributed array of values that have a certain increment. By the way, the default increment is 1, so if I say 0, semicolon 5, it'll increment by 1 from 0 up to 5. If I want a different increment than 1, then I have to explicitly state it, like so. Okay, so that's very, very useful. So very often we'll do things like x is equal to 1 to 5, right? That creates an array 1 to 5 with counting numbers. Sometimes you're not so interested in the actual increment as you are interested in the total number of elements in the array and the beginning and ending values. So let's look at this. X is equal to lin space. This means linearly spaced elements. I want to start at 0 and I want to end at 1, and I want 6 total elements. So here we go. 1, 2, 3, 4, 5, 6, starting at 0, ending at 1. So it just figured out that it needed to have an increment of 0.2. If I had said 7 elements, well, the increment would be 1/6. And so on. Okay, so lin space, we use this a lot. All right, so if I wanted to say, let's represent a sampling circuit that samples from 0 to 1 seconds and collects 1,024 samples. Okay, well, this is going to be a whole bunch of numbers, right? Big array, and I can generate that very, very easily. Now, another thing that you sometimes want to do is it's sometimes convenient to rearrange an array to change its dimensions. So let's say we have A is equal to I32 there, and now I want to change that array and manipulate it into a different matrix. So I can say matrix A 2, 3. Notice what it did. It rearranged those elements in a 2 by 3 matrix. Now, how did it do so? Let's look at another example. A is equal to 1, 2, 3, 4, 5, 6. And now we'll do matrix A. We're going to go from 2 by 3 to 3 by 2. So let's see how it rearranged things. Well, apparently what it does, you can see it goes through column by column 1, 4, and starts on the first column of the new shape matrix, but this one is going to be 3 by 2. 1, 4, then 2, 5, 2, and it's filled up that column, goes to the next column, 5, 3, 6, 3, 6. Okay, so I can reshape or rearrange the elements of an array. Arrays are not limited to having numbers entered as their values. We could do something like this. X is equal to 0.2, and C is equal to, left bracket, cosine of X, comma, sine of X, semicolon, minus sine of X, comma, cosine of X, end bracket. And those functional values will be entered as the elements of the array. This is very, very important. We'll use this many, many times. We can combine arrays. Let's take a look at this idea. V is equal to 1, 2, 3 as a row vector. Now what happens if I say A is equal to, start array with the left bracket, V, end array? Well, A will just be the same as V. How about if I say A is equal to V, and then comma, V? Well, Scilab says, well, this person wants to put V and then go to the next column and put V again. So you get V, 1, 2, 3, next column, and another V, 1, 2, 3. What if I said A is equal to V, semicolon V? Well, now it should give you 2 rows. The vector V, and then down to the next row, and the vector V. Okay, so you can stack vectors and arrays. In fact, A now, what if I did A, comma A? Well, I would get the matrix A alongside itself. Or how about if I did A, semicolon A, I'd get A stacked on top of itself, and etc. So to do that, the arrays have to fit together. So for example, let's see, here's V, and here's A. Can I do A, comma V? Nope, inconsistent. Why? Here's what A looks like, here's what V looks like. Notice, if I do A, comma V, it means, so put A and then go to the next column and put V, but V only has 1 row, so it doesn't fill up over here both of the rows. But if I, on the other hand, said A, semicolon V, well, that works because V has 3 columns and I can stack A on top of V and it all fits together. Right? But if I have U is equal to 4, 5, and V is 1, 2, 3, and I try to stack U and V, no, inconsistent, because U has only 2 columns and V has 3. On the other hand, think about this. So the problem here with the U stacked on top of V is U has only 2 elements. What if I do U, comma, 0? What would that do? Well, I'll get U, which will be 4, 5, and then comma, go to the next column, and a 0. So this will have 3 elements in the row. Now semicolon V, that works because I've spelled out a complete row of 3 elements, 4, 5, and explicitly the 0 there. I could also have said U, comma, 7, and I would get a 7 in that place. Okay, so as long as they fit together, we can stack arrays to form other arrays. All right, let's put an array in here. A is equal to 1, 2, 3, 4, 5, 6, 7, 8, 9. Now this array has a number of elements. In fact, this one has 3 by 3, right? Its length should be 9, 3 times 3, because its size is 3 by 3. Okay. What if I have this array and I want to change maybe the 6 here? I want to change that value, but not re-enter the whole array. Well, first of all, what if I want to just reference that value or figure out what is that value? Well, how do you index the elements of the array? Well, you give the row number and the column number. So this 6 is in the 1, 2 second row and 1, 2, 3 third column. So A, second row, third column is 6. And likewise, if I wanted to, I could assign a value. Maybe let's make that be 10. So notice what happened. That element that was a 6 is now a 10. And I can do that, of course, to any element. The first element, A11, I could make is equal to -1. and etc. So I can manipulate the elements in an array. I can fill them in either with a mathematical formula, or I can fill them in with some values that I measure or generate from a model, and then I can go and manipulate and change those. So that we'll use that extensively. Now here's something that looks a little strange, but is very, very useful. Very often we would like to extract or reference entire rows or columns. So let's say we want to take this column here with 2, 5, and 8, the second column of A. How can we extract that? Let's take a look. A, semicolon, comma, 2. Well, the first element corresponds to the row. Well, colon means step through all possible values, comma, and then we have the column. So all possible rows of the second column, well, that's just the second column, and there it is. It extracted the second column. Likewise, if we said A, 3, comma, semicolon, that would say the third row, all possible columns. So that should be 7, 8, and 9. We got to use this also like this: A, 3, comma, semicolon. So that's the third row. Let's assign different values. Let's assign -1, -2, -3 to that. And there you go. We just reassign the values of the last row. Then we don't have to extract an entire row or column too. We can extract submatrices. Let's say we wanted this first 2 by 2 submatrix, -1, 2, 4, 5. Well, that would be A, rows 1 to 2. So 1, colon, 2. That means step 1 and increment by 1 until you get to 2. So it would just be 1, 2, comma, columns 1 through 2. And there we've just extracted that 2 by 2 matrix. What if we wanted this matrix, 4, 5, -1, -2? Well, that would be rows 2 and 3, 2 to 3, columns 1 to 2. And there we extract that submatrix. Okay, so this array concept is very, very useful. First of all, we have this array here of 9 numbers that we could just refer to by the single name A. So that's the beauty of the bookkeeping. It's all these numbers are just collected in this one logical element, A, and then we can manipulate those elements, extract them, reassign them, stack them into different arrays, things of that nature. Now here's an interesting variation on that. Let's look at A again. What if we wanted to extract, say, the final 2 columns? We could have a new matrix, which is A. I want the final 2 columns, so I want all rows, so I could either do 1, colon, 3, 1 step from 1, increment by 1 up to 3, so 1, 2, 3, or as a shorthand, just colon means just go through all possible values, and I want the columns 2 through 3. So I could extract that matrix. But here's another thing I could do, and this is interesting. I could delete the first column. So I can do this. A, I want the first column, so all rows, first column, is equal to an empty matrix. I just deleted the first column. Maybe now I want to delete the second row of this new matrix. So the second row, all columns, I want to make an empty matrix. I just deleted that. So we can do lots of manipulations on arrays. Very, very useful. Let's say we had a vector 0 step by 0.2 up to 1, and I want to now reference one of the elements. Well, this is just, if we say size of t, it's 1 by 6. So I could say, what would I say, t13? Well, yeah, but in this case the 1's redundant in a sense because there's only one row. So notice I can do this. T3, Scilab lets me just forget that first element. I just want the third element of this vector. Likewise, if say u was equal to 1, 2, 3, 4 was a column vector, and I just said u3, well, it's the third element. In this case, it's the third row. Even though the size of u is 4 by 1, and you might think we need to say u31, the 1, I'm sorry, is redundant here. We can just say u3. So for a vector, we can just use one index, and Scilab knows that we don't need to put in the 1 for the row or the column. Now let's look at this. A is 1, 2, 3, 4, 5, 6. What happens if I say 1.5 times A? Well, in linear algebra, that should mean I just scale every unit in A by 1.5. Notice what happens. 1 times 1.5 is 1.5. 2 times 1.5 is 3, and etc. Yes, it's scaled every element in A. Likewise, I could say A over 2. Divide every element by 2. Okay, so that's perfectly valid. Now here's something that's a little bit non-standard, but it's sort of a shortcut. What would A minus 1 mean? Well, rigorously in linear algebra, this would be an invalid operation. A is a matrix, 1 is a scalar. You can't add and subtract matrices and scalars. But Scilab assumes that what you mean here is that I want to subtract the scalar 1 from every element of A. And so when I do that operation, notice what happened. Every one of these elements just decreased by 1. Okay, so that's sort of a shorthand, a non-standard kind of operation where you can add or subtract constant elements from everything in the array. You know, formally, if you wanted to do that in linear algebra, let's say we wanted to subtract 1 from every element in this array A here, we would say 1 minus 1's the size of A. Okay, so this is just a shorthand for that. Now on the other hand, so A here, right, is what? 2 by 3. Let's say B is equal to 1, 2, 3, 4 is 2 by 2. We try to say A plus B. Nope. Because A and B are both matrices now. To add matrices or subtract matrices, they have to have the same number of rows and columns. So you could certainly say A plus A or A minus A, which should be zeros, but you can't add or subtract matrices that don't have the same number of rows and columns. Now, oops, how about here's A and here's B. Let's look at this. B times A. Oh, that's interesting. We get a matrix there. B is 2 by 2, A is 2 by 3, and the result is 2 by 3. Interesting. Let's look at this. A here is 1 by 3. Let's say C is, let's make it 3 by 1. So we'll have three rows and 1 column. So say 3, 2, 1. A times C. Now A is 2 by 3 and C is 3 by 1. The product is 2 by 1. In general, if A has dimensions m by n and C has dimensions n by p, the product will be m by p. Again, we'll come back to this when we talk about linear algebra. So you have to have the same number of columns in the first matrix as rows in the second matrix, and then you can do the product. And this is just the product according to the rules of linear algebra, which we'll come back to. Now, another thing that's very common that you want to do in engineering, maybe you have 2 vectors. Oops. 1, 2, 3. So this is a column vector, and V is equal to 4, 5, 6. Very often we want to take the dot product or inner product of 2 vectors. What does that mean? Multiply 1 times 4 plus 2 times 5 plus 3 times 6. Okay, so how do you do that? Well, one way to do that is using the rules of linear algebra. We want to convert U to a 1 by 3 matrix, and then that times V, which is a 3 by 1 matrix, will give us a 1 by 1 product, which is the inner product. To do that, we got to change the form of U from a column to a row vector. Now that would be the operation we know as taking the transpose. So now let's look at this. U, single quote, that's the transpose operator. Actually, it's the transpose conjugate operator, but if they're real elements, it does the same as the transpose. So now we can take U transpose times V. We've got a 1 by 3 vector or matrix times a 3 by 1 vector, and we get 4 times 1 plus 5 times 2 plus 6 times 3 is 32. That would be the inner product. So multiplying arrays can be done according to the rules of linear algebra, provided they are of the appropriate sizes. Now we don't really have the concept of dividing by a vector or matrix, but we do have the idea of inverting a matrix. So let's take a look at this. A is equal to 1, 2, semicolon 3, 4. There's a 2 by 2 matrix. And let's say B is equal to a column vector 5, 6. We could look at this. X is equal to A backslash B. This is sort of like divide A into B. This is a solution to the equation AX equals B. In fact, let's check this out. A times X is indeed equal to B. So that's a shorthand for the, really what we're saying there is the inverse of A times B's. Okay, so that's the shorthand in Scilab and MATLAB for the inverse operation for solving a system of linear equations. And again, we'll come back to this in great detail when we talk about linear algebra. Now I want to talk a little bit about another really powerful aspect of this environment, and that is so-called vectorized functions. So let's clear everything off here and start over. Let's say I have x is equal to a big old vector, linspace 0 to 1 with 10 elements. Okay, let's make them a little more spaced evenly. Let's do 11. So there's nice. And spaced by 0.1. Okay, there we go. So suppose I want to go through and take the sign of each one of those values, right? So I could do this. Well, here x1 is 0. I could say sine of x 1. I could say sine of x 2. Right? And what if I wanted to save them? Well, I could have a new array. Let's say y is equal to 0's the size of x. Okay, and then I could say y1 is equal to the sine of x1. y2 is equal to the sine of x2. y3 is equal to the sine of x3. And I can just go through one after another. Now later we'll learn how to write so-called for loops which would allow you to automate this, but there's actually a nice shorthand in Scilab and MATLAB. I can just say y is equal to the sine of x, and Scilab goes through and fills in every one of those elements with the corresponding sign of the element in x. In other words, it knows what I want to do. I want this operation. What is the sign of a vector? Well, it's the vector in which each element is the sign of the corresponding element in x. That's called a vectorized function. That's very, very useful. We could even have a matrix. Let's say rand 3, 4, and I can say the sign of A. Well, it replaces each one of these elements by its sign. Okay, very useful. We'll get to graphics a little bit later, but here we have x, and we can do this. Plot x sine of x, and we very quickly get a little plot here. Let's make x bigger, so let's do x is equal to linspace 0 to 2 times pi 100 points. That's a big vector. Y is equal to the sine of x, and now plot xy, and there's the sine function. Okay, so we could do things very, very rapidly with this vectorization concept. Very, very useful, and we'll use it many, many times. Now, sometimes you want to do an operation that isn't a standard linear algebra operation. So say u is equal to 1, 2, 3, and v is equal to 4, 5, 6. One of the things we've already seen is if I say u minus 1, that's not a standard linear algebra operation. It's a vector minus a scalar. But Scilab knows that what you really mean there is you want to subtract 1 from each element of u. What if I have u and v here, and I want to go through and make a new vector in which the elements are 1 times 4, the second element is 2 times 5, and the third is 3 times 6. In other words, I just think of these as just a collection of numbers, and this is a collection of numbers, and I just want to multiply each of the corresponding pairs together. I could say z is equal to u dot times v. Notice what happened here. Here's u, here's v, here's u dot times v. 1 times 4 is 4, 2 times 5 is 10, 3 times 6 is 18. The dot is makes this an array operator. So u times v would be interpreted as the normal linear algebra operation, which won't work because u and v don't have consistent dimensions. They're both 1 by 3. You can't multiply a 1 by 3 matrix times a 1 by 3 matrix. But putting this dot operation in there overrides that and says I just want to go through and do this multiplication on an element by element basis. I could also do this. So here's u and here's v. U dot over v. Now what does that mean? Well, that means go through 1 divided by 4 is 0.25, 2 over 5 is 0.4, 3 over 6 is 0.5. So element by element I want to subtract. Here's our matrix A. Let's make a little simpler one here for illustrative purposes. Here's A. Now what if I say A squared? What does that mean? That's A times A. That's the matrix A times the matrix A using the rules of matrix multiplication from linear algebra. What I really want to do is I want to go through this array and just square each element. Well, that's not a standard linear algebra operation, but that's this array operation idea. A dot to the second power means go through A. 1 squared is 1, 3 squared is 9, 2 squared is 4, 4 squared is 16. So just operate on each element. So a non-standard kind of notation, but it's very handy because very often we were using these arrays really just as bookkeeping devices, not as formal vectors or matrices, that they might just be samples of something or some process, and we want to just go through and do this kind of operation where we're taking each sample times the corresponding sample in another array. Okay, now let's consider something like this. X is equal to 0 spaced by 0.1 up to 1. What if I want to sum all these values? So there are some special, well, obviously one of the things I could do is say x1 plus x2 plus blah, 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 and that would take a long time. But there's a special command, sum x, sum the elements of x. That's 5.5. Well, how many elements are in x? Length of x, 11. So the sum of x, sum of all the elements over the length of x, will be the average value of the elements in x. And there's a special command for that, the mean of x. There we go, 0.5. There's also things like max of x, min of x, and so on. Very handy little commands. What if I want, so here's x. A very common thing we want to calculate in engineering and in science, data analysis, is the mean squared value of a number of samples. So I want to square each one of these and then take the mean of those squared values. Well, that's the mean of, and this is the array operation I did, each one of these I want to square. So x dot to the power 2. Go through each element and square it and then take the mean of those. So there's the mean squared value. Root mean squared value, RMS value. Well, square root of the mean squared value, and so on. So we can do lots of calculations very simply. Here's a little subtlety that comes up. Let's say I have, let's make u, here's 1, 2, 3. I want to do the array operation where I'm going to say 1 over each one of these elements. So I want to have 1 over 1 is 1, 1 over 2 is a half, 1 over 3 is a third. Let's look at this. 1 over u. Didn't quite work. That's interesting. Let's try this. 1.0 over u. Okay, that doesn't work either. Well, it shouldn't, because in fact this is not an array operator. We're not saying go through element by element. We don't have the period in there. Okay, so let's put the period. 1 period over u. Oops, it tells you, warning, 1 period backslash is interpreted as 1.0 over, so it's the same as 1 over u. And this actually is a thing called, related to what's the so-called pseudo-inverse of this vector. We'll get to that later. But it's not the array operation we want. We have to be careful to make sure that Scilab doesn't think this we mean 1.0 over something. So we say 1 space dot over u. And now we get the array operation. 1 over 1 is 1, 1 over 2 is a half, 1 over 3 is a third. Or we could have said 1 dot over u, or somehow we have to make it explicit that we don't mean 1.0 over u. So far we've looked just at real array elements. We can have complex array elements like this. A is equal to 1, remember %i, that means the imaginary unit, down to the next row, 2 minus I. So there is an array with complex elements. A squared is an array with complex elements. So here the first element is 1 plus 2i, in the first row, second column, 1 plus I, and so on. So that's a complex array. We can do things like get the real part of it, real part of A, that'll strip out the real parts. So here's A. So real part of A is just 1, 2, first column. Imaginary part of A, minus 1, 1 minus 1 in the next column. Here, let's see, B is equal to A squared. Real of B will just be these real parts, 1, 2, 1 minus 1, and imaginary part of B will be the 2 minus 2, 1, 2. Now, here's A, and let's do A, single quote. This is the transpose conjugate operator. So what does it do? It transposes the matrix. It takes the off-diagonal elements and flops them over. So the 2 goes from down here up top, and the I goes down below, but it also changes the signs of all the imaginary units. That's the conjugate part. So that's transpose conjugate. If this was a real matrix, like C is equal to 1, 2, 3, 4, and we do C transpose conjugate, well, that's just the transpose, because the conjugate of a real number is just the real number. But going back to A transpose conjugate. What if we only wanted to transpose A? We didn't want to conjugate it. This is a special command, A dot single quote. So there's your A, and now all you've done is just flipped these two off-diagonal elements. Okay, so that's transpose conjugate and the simple transpose operation. Okay. Now, so far we've looked at arrays of numbers. We can have arrays of strings, like this is an array of strings. This is an array of strings, okay? How about an array that has a number and a string? No, doesn't like it. They have to all be of the same type. So that brings up a different type of array structure, which we actually call just a structure. So structures are kind of a more generalized form of an array. If you want to think of it that way, we might say ST is equal to structure, and then we have fields and values. So we might say something like, well, name, and let's say the name is ball joint, and then another property which will be mass, and this could be a numerical value, 2.7. So there's a structure. It has two fields. One is called name, which has the value ball joint. The other is the field mass, which has the value 2.7. And to pull out one of those or reference one of those, I can say st.name is ball joint. If I want to change it, st.name is equal to new joint. Okay, I've just changed that value. How about the mass? st.mass is 2.7. And I can say st.mass squared is 2.7 squared, or st.mass, change it to 7.2, etc. Okay, so that's a structure. It's a way to combine various different fields, which can have names and values, and they're not limited to all being numbers or all being strings or what have you. So they can be strings, numbers, they can even be arrays. For example, let's take a look at this. Body equals structure. The first field is going to be called pause for position, and let's say it's the vector -203. That's a vector position, say. Next one is angle. It might be 12, -20, 28. In fact, a solid body is completely specified, its orientation in space, by giving the position of its center of mass and 3 angles, rotation angles, about that center of mass. So here would be a structure that could represent a solid body. So if I wanted to, this maybe is the x, y, and z coordinates of the center of mass. If I wanted to change the z coordinate, I could say body dot position 3 is, see right now it's 3, so I could go back and say let's make it 7. Okay, so this now position is an array, and this is a one-dimensional array. A vector could be a matrix too. Moreover, you can make arrays of structures, which is kind of a neat idea. Let's look at this. Let's say we wanted a simple database of customers, something like that. So we might make a structure called person equals structure, their name, okay, and I'll just initialize that to nothing for now, and their age, which I'll initialize to 0. So there's a structure which has a field called name and a numerical field called age. Now I could say member is equal to, and I'll make an array of persons. Person, comma, person, comma, person. This is a 1 by 3 array of structures. So now I could say member 1. Okay? Member 1, there's a place for a name and a place for an age. So I could say member 1 dot name is equal to Tom. How old is Tom? Member 1 dot age is equal to 24. Member 1, there's our data. Member 1 is Tom, age 24. How about member 2? Well, no one's been entered there yet. Member 2 dot name is equal to Mary. Member 2 dot age is equal to 27. Now member 2, I can look at all the fields of member 2 and etc. Okay, so this is a very common type of operation. So it's sort of a higher level of bookkeeping abstraction than an array itself. It's sort of generalization of that. It's even possible to have structures which serve as fields of other structures. So let's look at this. Book is equal to a structure that has a field labeled title. Right now, I'll leave that blank till we actually assign something to that, and another field called author. Leave that blank. Then we could have a structure called class. It's a structure that has a field titled name, which I'll leave blank, and then it has another field called text, and this is itself a structure of type book, which we just previously defined. So now I can take class dot name, so the name of the class, now I'm going to assign a value to it, is equal to English 101. Then I can say class text. Okay, so class text, but text itself is a structure that has fields, so I have to figure out which one of these fields I want to specify. So let's say dot title. Class text title is equal to, oh, I don't know, how to write. Okay, and then I could say maybe class text author is equal to K. Smith. And now class.text, you can see, is a structure title how to write by author K. Smith. class name is English 101. And then I could make arrays of these classes. All right, so you can see there are all kinds of ways you could combine these things to make very, very complex sorts of data structures, essentially. Actually, you don't have to go through this assigning of these structures to start. Let's clear everything out and start over. I could just say class.name equals intro psych. That creates a class with a field called name, which has the value intro psych, and then I could say class enrollment equals 24. Here's class. Well, now I've just added that. Let's maybe say class dot tests equals 3. There are going to be 3 tests in this class, and so on. So I don't have to initialize or specify the fields up front. I can just dynamically add them as I go along. So that's the concept of a structure. We won't use it a whole lot. Very useful when you start to write really big programs, right? So you could imagine, for example, having a physical mechanical system that had many components and degrees of freedom, was very complicated to describe. You could put that whole thing into one structure. So you could have one logical entity that held your just complete description of your entire system. And then you could operate on various components of that and so on. So a very useful way to organize information.